Hey everyone, welcome back to our Foundations of Data Systems Explainer. Today we're diving into part 14, which is all about column-oriented databases. Now, if you've ever watched a data warehouse crunch through millions of rows in literal seconds and thought to yourself, wait, how is that even physically possible? Well, you're in the exact right place. We're going to look under the hood to see exactly how column-oriented databases are uniquely designed to just absolutely crush massive analytics workloads. Let's get into it.
Here's our quick roadmap for today. We'll start with the analytics query problem, look at row-oriented storage limitations, and then enter column-oriented storage. From there, we'll explore the power of compression, faster processing and aggregation, and finish up with choosing the right tool.
All right, section 1, the analytics query problem. Let's talk about scanning millions of rows.
So here's the central dilemma you're going to face when building data-intensive applications. How do we scan millions, or honestly, even billions of rows without completely crashing the system or, waiting hours just to get a single result back? Picture a hypothetical sales analytics query. You need to calculate the total revenue by region, and you have to do this across millions of individual orders.
To really ground this technical challenge in reality, think about those business intelligence dashboards that modern companies completely rely on. When a business analyst runs a query to find out, say, exactly how many bananas sold during a recent promotion, they are aggregating massive amounts of historical data into a simple, readable report. They aren't looking up one single user, they are crunching deep history.
And here is the really crucial point. A massive fact table in a data warehouse might have well over 100 columns. But our analytics query, it actually only needs a tiny handful of them. For our banana promotion, we might only need the date, the product ID, and the quantity. And that's it. We want to completely ignore the other 90-plus columns.
Which brings us to section 2, row-oriented storage limitations. Let's compare OLTP and OLAP. To really understand where the bottleneck is, we have to contrast OLTP with OLAP. Online Transaction Processing, or OLTP, is the engine powering your interactive web apps. It fetches small, random access records super quickly using a primary key. Online Analytic Processing, or OLAP, is an entirely different beast. It focuses on heavy, historical data scanning and aggregating huge chunks of records all at once. Now, traditional databases default to a row-oriented storage layout. That means the entire row is stored contiguously, right next to each other on the disk. This is brilliant for OLTP when you just want to fetch a single user's profile, but it's an absolute nightmare for our OLAP analytics query. Why? Because it literally forces the disk to waste massive amounts of time loading over 100 useless columns into memory just so it can filter them out to find the 3 columns we actually care about. It's a staggering waste of disk bandwidth.
Let's move to section 3, enter column-oriented storage, flipping our data layouts.
Take a look at the fact_sales table at the top of this diagram and compare it with the columnar layout right below it. Notice the shift? Instead of storing all the values from one row side by side, a column-oriented layout completely flips this. It stores all values from the exact same column together in a single file. So all your date keys are bundled in one file, all your product keys in another, and all your quantities in yet another.
The immediate performance win here is just monumental. We only read the exact columns we need. If our query only requires the quantity and net_price columns, the storage engine only bothers to read those 2 specific files from the disk. We completely bypass loading all that other irrelevant data, saving an incredible amount of disk I/O bandwidth.
Now you might be wondering, hold on, if we separate all the columns, haven't we kind of lost the concept of a row? Actually, no. Reconstructing rows is surprisingly easy because the whole layout relies on identical ordering. We know for a fact that the 23rd entry in the date file belongs to the exact same row as the 23rd entry in the quantity file. The database just dynamically reassembles the row by grabbing the value at the exact same index position across those different column files.
All right, section 4, the power of compression. Let's talk about crushing data size.
Because columnar layouts inherently group similar data together, the values inside a single file end up being incredibly repetitive. And repetition makes them absolutely right for advanced compression techniques. One of the most powerful ones is called bitmap encoding. This transforms a column of repetitive values into highly compact sequences of distinct Boolean bits. Look at the product SKU column at the top here. A massive retailer could easily have billions of rows of sales, but maybe only 100,000 distinct actual products. We can take that column and turn it into separate bitmaps, one specific bitmap for each distinct product value. As you can see, the bit is simply a 1 if the product exists in that row and a 0 if it doesn't.
And because a specific product only appears in a tiny fraction of total rows, these bitmaps are what we call sparse, meaning they are overwhelmingly full of zeros. We can then use a trick called run-length encoding to crush those long sequences of zeros down even further, literally turning massive columns into mere kilobytes of data. Just to put that into perspective, you could shrink a gigabyte of repetitive sales data down to the file size of a simple text email. Plus, the database can execute complex where clauses, like checking if a product is X or Y, using incredibly fast bitwise and/or logic operators right there on the compressed bitmaps.
Moving on to Section 5. Faster processing in aggregation. How this optimizes for the CPU. When it comes to calculating aggregates, a columnar database follows a really rapid sequence. First, it locates the specific column files it needs. Second, because that data is so highly compressed, it can actually load large chunks of it directly into the CPU's L1 cache, which, if you know your hardware, is the processor's absolute fastest, closest memory. Third, the CPU iterates through this data in a super tight processing loop.
This whole technique is known as vectorized processing. By avoiding complex function calls for every single record and instead leveraging SIMD instructions, that stands for Single Instruction Multiple Data, the CPU operates on these compressed chunks directly. It calculates totals, averages, and counts at absolutely blistering speeds, all because the data layout is perfectly aligned with the physical hardware.
Finally, Section 6. Choosing the right tool. Let's bring these system design takeaways together.
As a system architect, you absolutely have to understand the trade-offs. Columnar databases are heavily optimized for read-heavy analytics. You can even sort the rows by a common column, like the date, to create longer runs of the same value, which drastically improves your compression. But there's a catch. Writes are tricky. You can't just shove a new row into the middle of a tightly compressed file. So columnar databases often use an in-memory buffer, like an LSM tree, to collect those writes first before carefully merging them to the disk.
This cheat sheet right here really drives home the golden rule of database architecture. You must match your storage layout to your workload. If your app handles fast, single-record transactions, you want row-oriented storage, where your main bottleneck is just disk seek time. But if you're aggregating huge datasets for analytics, you absolutely want column-oriented storage to elegantly solve that disk bandwidth bottleneck.
Which leaves us with this final thought. The next time you find yourself staring down a dashboard that is taking literal minutes to load, I want you to ask yourself, are your slow queries actually a symptom of bad code, or are you simply using the wrong storage engine for the job? Thanks so much for joining me for this explainer. Keep evaluating your bottlenecks, and we'll see you in the next one.